In this lecture, we are going to deal with a method of handling systems, equilibrium of those systems which are large and have a large number of subsystems. The method is known as method of virtual work. To motivate this, let us recall how we dealt with equilibrium of systems such as particles, trusses, and so on. Our strategy in those cases was to look at subsystems and make free body diagram of subsystems, replacing the constraints or the forces applied by others or the contact with other subsystems by the forces applied by them, and balance all forces and torques. However, as the system size grows, the number of forces, number of subsystems may grow quite large, and in such systems the method that we use is the method of virtual work. The method focuses directly on the external force that we want to calculate. To motivate it further, let us take an example. Suppose I have a mechanism whereby made up of two bars, whereby it is a scissors like mechanism with a pin joint here and a roller here, which is free to move in this between these two walls. Each bar has a mass m, and this is kept in equilibrium by applying a force F at this point. If we want to calculate the force F, our strategy is we first look at this mechanism. On this point there can be only one force, let us call it N B. This is point B, this is point A. This is a pin joint, so there could be a force N 1A and N 2A. The force F acts here, and the overall weight 2 mg pulls it down. If we were to bring this in equilibrium by summation Fx equal to 0 would give me that N2A plus Nb equals F. That is one equation. Similarly, summation Fy equal to 0 would give me N1A equals 2 mg. Remember what we are after. We are after calculating this force F required to keep the entire system in equilibrium. Third, the torque equation. For the torque equation, I will take torque about point A here. Let me make it by blue. I will take torque about this point, so that torques due to N1A, N2A and F all vanish. So, if I take torque about A to be 0, I get, if the length of half of the bar is B, right. So, I am taking this half length to be B, and let this angle, entire angle, be theta. Then while calculating torque, I am going to get N B times this angle here is going to be theta by 2. So, I am going to get B cosine theta by 2 times 2 that is this arm, plus 2 mg b sin theta by 2 is equal to 0, and that gives me NB. B drops out, this 2, oh no, so this 2 is there, this 2 drops out, and therefore I get NB to be, I had NB cosine of theta by 2 plus mg sine of theta by 2 equals 0, or I get NB to be minus mg tangent of theta by 2. Therefore, if I look at this mechanism that we had made earlier, this is a pin joint here, this is on a roller that is free to move in this. I have a force F acting this way, 2 mg pulling it down, NB we have just calculated is mg tangent theta by 2. Notice that because of this negative sign I have already corrected the direction of mg, and there is N1a and N2a. Now to calculate F, I look at one of the rods individually, this one. Here is a force F pulling it this way, its own weight mg pulling it down. There is a force normal reaction here which we have just calculated, mg tangent theta by 2, and now there are going to be normal forces due to the pin out here. Let us call this N1 and N2. If I am just interested in calculating force F, then you can see that I can take the torque about this middle point, the pin here, let me show this in blue, about this point, and calculate F to be equal to, by taking the torque about this point, let me call summation, torque about this point is 0, and therefore F times whatever this length is, call it L, minus same length is going to be here, mg tangent theta by 2L equals 0, and F equals mg tangent of theta by 2. So, we found the force F. If you are interested, you can also calculate N1, N2 and other normal forces, but our main focus was to calculate F, and that is what we have found. Notice that we had to take several steps in getting to this answer. If we use method of virtual work, as I will show later, all these steps are bypassed. Not only that, if I were to solve the same problem about the same mechanism, but make it slightly more complicated, in that now I have several of these links. And I apply a force here. Each link, each of this bar has mass m and length 2b, and I want to calculate the force F to keep this whole thing in equilibrium. You see, if we go the conventional way, I will have to build up the solution step by step by step. With method of virtual work, we will be able to do it in a much more easy manner. So, to develop the method, we need certain terminologies. Let me now go over them. So, now we are going to go over some terminologies that are going to be used in the method of virtual work. First, let us define degree of freedom of a system. The degree of freedom of a system is the number of parameters, and it will be clear when I give an example, required to specify the position, the orientation and all that, the system. So, when I say specify the system, I mean precisely that. What is its position, what is its orientation, at what angle is it from vertical, and so on. So, for example, if I take, so we are talking about degrees of freedom. Again, number of parameters required to specify a system. For example, if I take a particle in 3D space, the number of degrees of freedom is 3. If I take a particle constrained to move only on a plane, constrained, and I'll make this definition constraint clearer a little later, constrained to move on a plane, then the degrees of freedom are 2. Suppose I take a pendulum so that it swings in a plane. The only thing that I need to specify where the pendulum is this angle. Then the degree of freedom is 1. Even in the complicated example that we took previously for that mechanism, whereby I had these cross links like this, the only thing that I need to specify the orientation or a specific position of the system is this angle theta, nothing else. The moment I specify this theta, because the lengths of these bars are fixed, I specify exactly how the system is. So degrees of freedom in this case is also 1. So this is one concept we are going to use. The degree of freedom specifies the parameters used to describe a system and the complexity of the problem. Less the number of degrees of freedom, less complex the system is. Concept number 2, constraints. This we have been talking about while talking about equilibrium, but let me go over it in a formal manner now. Constraints and constraint forces. By constraints, we mean the restrictions on the movement of a system. For example, if I take a particle and constrain it to move only along, say, a wire, then that is a constraint that is put in, that it can move only along a straight line. Or if I take a particle, put it on a plane and constrain it to move only on a plane, this puts a constraint on the particle to move only in this plane. Similarly, if I take this pendulum example that I took, the constraint is that the distance of the bob hair of the pendulum is fixed from the pivot point. So you see, we are putting constraints whereby we restrict the motion. And what does a constraint do? A constraint reduces the degrees of freedom of a system. For example, in the case of a pendulum, number 1, the pendulum is to move in a plane, so degrees of freedom are 2. Then I put a constraint that the distance of this bob from the pivot point is fixed, so I reduce the degree of freedom by 1 by putting one constraint, and finally the degree of freedom therefore comes out to be 1. How do we put the constraints on a system? We put constraints on a system by applying certain forces. For example, here a force that is related to the constraint is the tension in the string. In a motion on two-dimensional plane, the constraint force is the normal reaction on the particle due to the surface. It would not, that normal reaction doesn't let the particle fall below and go make a motion in the direction perpendicular to the surface. So these are known as constraint forces. These are forces that put in the constraint. on the motion. One of the very familiar constraint that you have come across time and again is the rigid body. This is a concept we keep using. In a rigid body, the constraint is that distance between any 2 points always remains fixed. And what is the constraint force? The constraint force is that internal force that keeps the distance fixed. All right. So, the concepts that we have come up with are the constraints. Okay. This result is that reduces the degrees of freedom, and constraint forces, okay, they enforce the constraint. Let us go back to that example of that mechanism whereby these bars were making the mechanism and so on. What are the constraint forces here? The constraint forces are the normal reaction here, both in vertical and horizontal direction, the normal reaction here, and the forces that are applied by the spin. It is these forces that make the system move in a particular way. It reduces degrees of freedom, and degrees of freedom finally is only 1 given by this angle theta. Note, and this is very important to develop the method of virtual work, is that constraint forces usually do not perform any work on the system. Why do I say usually? Because I am going to exclude a particular constraint force a little later. So, take the example of particle on a 2-dimensional surface. The constraint force normal reaction is perpendicular to the surface, the particle moves along the surface, and 2 are perpendicular. So, normal does not do any work on this. Take the example of the pendulum. The constraint force tension is always perpendicular to the direction of motion of the ball, and therefore, this also does not do any work. How about this mechanism? The point here, A point, does not move at all, and therefore, no work is done by the normal forces at this point. The normal reaction at this point B is perpendicular to the direction of motion, and therefore, that also does not do any work. How about the forces due to the pins here? You see, the pins apply a force on one particular bar in one direction and exactly opposite force on the other bar. However, the pins move by exactly the same amount. So, bars also move exactly in the same direction, but the forces are opposite. The result is that the net work done because of this constraint forces is 0. It is positive in one bar, negative in the other bar, added up it gives me 0. So, you see, I have given you 3 examples where you see that constraint forces usually are not performing any work. Why I say usual is, this is, if we have a frictional force as the constraint force, that does perform work when the system moves. Therefore, if we include friction, then I would say constraint forces usually do not perform any work. On the other hand, if I exclude friction, then I will take you here and cut this off. Then I would say that constraint forces do not perform any work on the system. In my development, now, we will be excluding friction and deal with those constraint forces that do not perform any work on the system, and it is this observation that makes dealing with the system very easy. Next, I want to develop the concept of virtual displacement. In virtual displacement, I would like you to imagine, and I want to emphasize this word imagine, the displacement of a system under equilibrium, and the displacement is such that displacement is consistent with the constraints. So, what you are imagining is, suppose there is a body which is in equilibrium. Let us again take an example. If I take the pendulum and suppose I apply a force this way, F, its own weight mg, and it is in equilibrium. Imagine, just imagine that I displace it slightly. This is the only way I can displace the pendulum. No other way, because this is the only degree of freedom allowed, that is, I can change only theta. So, this displacement is consistent with the constraint, but it is actually not moving. I am imagining as if it has moved, and this is known as virtual displacement. So, and it is usually given by the symbol delta. So, delta theta virtual movement or displacement. On the other hand, if I moved the bob along the string, the length of the string would change, and that motion would not be consistent with the constraint condition. Therefore, I cannot call that motion a virtual motion. So, virtual displacement is again is an imagined displacement of systems, subsystems consistent. So, imagined displacement of a system consistent with the constraints. I have already given you the example of the pendulum. This mechanism again, if I go back to, the only way I can change its configuration is by changing the theta. So, if it is in equilibrium under this force F here and its own weight, the virtual displacement would be delta theta. One thing I should make it clear, I am writing it delta theta. So, virtual displacement is also very small displacement. The change is very small. You imagine a very small change. So, it is about equilibrium, a very small change which we imagine, and that is a virtual displacement. Next, associated with virtual displacement is something called the virtual work. So, when you are making a virtual displacement, each particle in the system is changing its position. So, virtual work by a force is force times delta r, where delta r is the virtual displacement. Naturally, if I am doing a displacement consistent with the constraints, and we have already seen that the constraint forces do not do any work. So, virtual work done by constraint forces is equal to 0. This is a very important statement, and that makes the development of method of virtual work possible. With these definitions, we are now ready to develop the method of virtual work. So, in method of virtual work, we state that the necessary and sufficient, both necessary and sufficient condition for a system to be in equilibrium is that the virtual work done by externally applied forces vanishes. Two comments are in order. One, that we are talking about system which has no friction. If friction is included, then the constraint forces also do, the frictional constraint force also does some work that we are excluding. Then because of the vanishing of work by constraint forces, it is only the work done by externally applied forces, those which are not constraint forces, but the forces that we apply from outside to achieve equilibrium. Then the virtual work done by externally applied forces vanishes. Notice we have avoided taking constraint forces into account, and therefore, when we apply this method, we can bypass calculating the constraint forces. Let us see how this method works. So, condition for equilibrium of any system is that summation of all forces on any particle, ith particle, summation of all forces be 0. This may include the externally applied forces on the ith particle plus F on ith, which are constraint forces. Their sum is 0. If each particle is in equilibrium, the system is in equilibrium. Now, let us calculate the virtual work done. Virtual work done is going to be F external I dot delta Ri. This summation refers to all the forces that are applied, plus summation Fi, I refers to the ith particle, constraint dot delta Ri is equal to 0. It is 0 because right hand side is 0. However, we have already said that constraints do no work. Therefore, this second term vanishes, and this tells you that the work done by all the external forces together on each particle is 0. If the work done on each particle is 0, the net force, therefore, summation over I is also 0. Implies delta W, the virtual work external, is 0. We have proved the sufficient necessary part of the principle of virtual work. How about the sufficient condition? As I said, it is also a sufficient condition. So, if the forces on all the particles Fi external plus F constraint I, suppose they do not vanish. If they do not vanish, then the system or each particle would tend to move in the direction along which this force is, and therefore, F external I plus F constraint I dot to distinguish from virtual displacement, I am writing this as dRi for each particle would be greater than 0. It is greater than 0 because force would make the particle move in the same direction in which it has the net direction. However, now in virtual work I can imagine the system being displaced virtually by delta Ri. So, F external I plus F constraint I virtual will also be greater than 0 for each particle. If this is greater than 0 for each particle, the summation over I would also be greater than 0. So, the work cannot vanish. If the work vanishes, that means that this sum must be 0. Again, we are going to use the fact that the work due to constraint forces is 0, and therefore, again summation F external I is greater than 0. Applying the same argument, if this is non-zero, under the condition that system is not in equilibrium, if this is 0, system must be in equilibrium. So, that also proves that it is also a sufficient condition. So, now we are going to take it from there that the principle of virtual work is, I will write this in symbols, the virtual work done by external forces is equal to 0 at equilibrium. And that is sufficient to determine the forces and so on. Let us take an example. I will start with the pendulum example. This angle is theta. This pendulum is supposed to be under equilibrium, in equilibrium under the applied force F and the weight of the bob mg. This has 1 degree of freedom. So, I can make a virtual displacement changing that theta only here. The principle says that delta W only external forces is equal to 0. The only external forces that are working on the system are F and mg, with T being the constraint force which does 0 work. So, this is only external. Let us make a virtual displacement of delta theta. If I make a virtual displacement of delta theta, let us calculate the work done, virtual work done by force F and force mg. When I make this displacement, if the length of the pendulum is L, then the bob moves up, let us call it delta y, by an amount L sin theta delta theta, and it moves in the horizontal direction by L cosine theta delta theta. In fact, I should put this negative to show that it is moving up. So, the virtual work done is going to be, let me make the picture again, this is the bob at an angle theta. I change this to a virtual position theta plus delta theta, then delta y is moving up minus L sin theta delta theta, delta x is L cosine theta delta theta. The force this way is F, force this way is mg. So, this minus sign in delta y actually refers to this being opposite to mg. So, delta W is going to be F L cosine theta delta theta minus mg L sin theta delta theta, and by principle of virtual work this should be 0, and that gives me F equals mg tangent theta straight away. You see, I did not have to go to calculate the tension, whereby I would have written T cosine theta is equal to mg and T sin theta is equal to F, and therefore F equals mg tangent of theta. Let us take the other example that we took in the beginning with this mechanism here. Which is in equilibrium under this applied force F, its own weight is 2 mg, and the only angle that matters here for the degree of freedom is this theta. Each side, each half of the bar is B. The constraint forces again do not do any work, and therefore, delta W, external forces only, should be 0. The two external forces that are there are F and mg. Let us make a virtual displacement of the system. What would a virtual displacement be? Virtual displacement will be to make this angle larger. If I make this angle larger, what I will be doing is pulling this point out. Let me show it by red. This point will be going out and this point would be moving up. By how much amount? Let us calculate that. So, this distance here is nothing but, let us call this y, and let this distance from here to here be x. Then you see that y is equal to b. Okay, let me show this angle here. This angle is going to be theta by 2. So, y is b cosine of theta by 2. If I change theta slightly, delta y is going to be delta of b cosine of theta by 2, and that is going to be b over 2 sine of theta by 2 delta theta. This is the virtual displacement of the center point if I change angle to theta plus delta theta. Similarly, x is equal to b sine theta times 2, this entire distance, and therefore, delta x is going to be, this is 2b sine theta by 2, 2b 1 by 2 cosine of theta by 2 delta theta, which comes out to be b cosine of theta by 2 delta theta. Why we are calculating these delta x and delta y is so that I can calculate the virtual work done by force F and 2 mg. Let me make the picture again schematically, and we have calculated that delta y is nothing but minus b over 2 sine theta by 2 delta theta, and delta x is equal to b cosine of theta by 2 delta theta. By minus sign, we mean that y is decreasing, or the point here is moving up. So, delta W is going to be equal to the work done by virtual work done by force F. Since x has increased by b cosine theta by 2 delta theta, work done by F is going to be F b cosine of theta by 2 delta theta, positive, because the point here has moved in the same direction as the force, and the work done by the force mg, or the weight, is going to be minus 2 mg b over 2 sine of theta by 2 delta theta, and this should be 0. You calculate this and you get F equals mg tangent theta by 2, and that is your answer that we had obtained earlier. Notice I did not have to go through calculating the normal forces and things like those, which we avoided and bypassed because of the work being virtual work being done by those normal forces or constraint forces 0. How does this simplify or make life easy when the system becomes big? Let us extend this example itself. In this mechanism, if I take many links, suppose n such links, and so on, and I apply a force F here. Each bar is mass m, and I want to calculate how much force F is required to keep this entire system in equilibrium. Again, notice that the system has only 1 degree of freedom, with this theta describing everything. Let the length here be b. Imagine again a virtual displacement of the system, so that theta goes to theta plus delta theta. If that happens, all these points are going to move up. And all these gaps here are going to widen up. We have already calculated that delta y for each point is equal to b sine of theta by 2 delta theta, b divided by 2, and delta x for each of this gap opens up by b cosine of theta by 2 delta theta. So, if there are n such links, delta x for n is going to be n times as much, n times b. Delta y for each joint is going to remain the same. So, work done, virtual work done is going to be n b cosine of theta by 2 times f delta theta minus this delta y at each link is doing work against 2 mg, and there are n such points. So, therefore, I am going to have n times 2 mg times b over 2 sine theta by 2 delta theta, and this should be 0. This n drops out, 2 cancels, so does b, and so does delta theta, and therefore, you again get, and let me write it here to keep on the same slide, f equals m g tangent of theta by 2, same answer as earlier. So, we figure out that no matter how long a link do we make, it does not matter, the force required to keep the system in equilibrium is still mg tangent theta by 2. But you see how easy it was. We did it in 4 or 5 steps using method of virtual work. So, let us recap what we did in method of virtual work. 1, imagine, and I keep using this word imagine because this refers to a displacement which you imagine, it does not really take place. Imagine a virtual displacement or virtual change of orientation and so on of a system. 2, calculate the virtual work done by external forces, and 3, call this delta w. Delta w is equal to 0, gives the equilibrium condition. As in any other new concept, to master it, you have to keep doing many problems, and I will again rest of the lecture I am going to do 3 or 4 more examples to make you more familiar with the method of virtual work. These examples are from the book by Shames on engineering mechanics and book by Merriam on statics. As the first example, let me take a crane on which there is a shaft here and by a string by applying tension T, one is holding a weight W. The distances given are 4 meters, 4 meters and 3 meters. We wish to calculate, given tension T, how much weight can be held here in equilibrium. Let me call this angle theta and this angle alpha. If I want to use the method of virtual work, then what we should do is imagine a virtual displacement of the system, and here the virtual displacement is going to be described by the change in angle here. As you change, you pull this string in or pull the rope in, this system is going to move like this. So, virtual displacement is going to be change in theta, and then calculate the work done by the external forces W, and notice in this case the external force tension is not a constraint force. The constraint force is the force provided by the shaft because of its rigidity. So, the work done by that is going to be 0, because the displacement is always going to be perpendicular to the shaft, and so we have to calculate work done by W as well as T, the tension, and make it equal to 0. So, let us see, at the given position where the distances are given to be 3 meters, 4 meters and 4 meters, what we have is virtual displacement is going to correspond to delta theta, and that will make this point move up both in x direction and y direction. So, what we have the situation schematically is theta alpha 4 meters, 4 meters, 3 meters, W here, tension T here. When I change theta to delta theta, if this length is going to be 5 meters, this is 3 and 4. So, delta y positive in the up direction is going to be 5 delta of 5 sine theta, which is going to be 5 cosine of theta delta theta. Similarly, delta x is going to be in the negative direction, x is going to decrease. So, I am going to write this as negative, or just keep in mind it is to the left, is going to be 5 or delta of 5 cosine theta. Which is going to be 5 sine theta delta theta. Towards the left, we have calculated both x and y components, and therefore, the total work done delta W is going to be the weight and delta y in opposite direction. So, minus W delta y. The T has a vertical component at this point going down, which is going to be T sine of alpha delta y, and T has a component going towards the left, which is T cosine alpha. So, that is going to be T cosine of alpha delta x is equal to 0. This gives me W delta y. We have already calculated 5 cosine theta delta theta. 5 cosine theta from here is 4 times 4 delta theta minus T sine alpha. Sine alpha is going to be 3 divided by this length, and this length is 8 square plus 3 square square root. So, root 73. So, T times 3 over root 73 times 4 delta theta plus T cosine alpha is going to be T, or this is a minus sign here, T cosine alpha is going to be T 8 over square root of 73, delta x is in the same direction, 5 sin theta is 3, 3 delta theta is equal to 0. And that gives you, I can cancel the 4, 4, 4, and this will give me 2 here, and that gives you W is equal to, so 3 over root 73 t. That is the weight that can be held by this machine. You see, again the calculation was very straightforward. As the final example of applying the method of virtual work, I solve a problem that involves both a force and a torque. The example is that of a screw jack, whereby two supports like this are fixed the screw here, and we apply a torque here C. These go down and are fixed on a stand. One of these links is fixed and the other one can move in a slot, and same thing on the top. One of them can move in the slot and the other one is fixed. The question that we ask is, if there is a load W on this jack, what is the minimum torque C that is needed to lift this weight? So, weight W to be lifted is to be lifted by applying a torque C. You are given that this angle is theta and so is this, and this length is B. Let us also call these points A, B, C. You can again see that there is only 1 degree of freedom, and that is angle theta. Question is, how do we calculate the force that the torque required so that this force W or the load W is balanced or can be lifted? To calculate this, let us see what happens when we rotate the screw. In rotating the screw, the length between A and B, that is these 2 points, gets reduced by the pitch of the screw for a full rotation. So, what is given when I make a full rotation, that is 2 pi rotation, the distance AB becomes smaller by L, the length L, which is the pitch of the screw. When A and B come closer, this platform gets lifted because this point gets lifted. So, in rotating the screw I am doing some work, and in lifting this another work is being done. The external forces and torques now are C, the external torque, and W, the external load. The net virtual work done by combination of C and W should be 0. Let us calculate that and make that equal to 0. Let us call this angle theta, which has already been given. So, when the length reduces, the theta becomes slightly larger. Let us say this goes to theta plus delta theta, and therefore, this length between, let us call this AB and the top of the triangle C, and the perpendicular distance from C to AB CD. So, this D, C, A and B, CD increases. The total length would increase by 4 times the increase in CD, because there are 4 gaps like these. So, let us calculate that. Let us call this distance AD x. So, that delta x is the reduction in the length, and delta x is going to be L over 2 pi times delta alpha, where delta alpha is the rotation of the screw. So, now what we do is imagine a virtual displacement consistent with the constraints. And that virtual displacement is going to be rotation of the screw by an angle delta alpha, and that causes shortening of the distance between A and B and increase in the distance C and D. From that I can calculate the virtual work done by applying the torque and the virtual work done against the weight, and making the sum total of that virtual work 0 would give me a relationship between the torque C and the weight W. Let us calculate that now. So, in this triangle A, B, C and D, let us call this distance x and this distance y. This angle is theta. Let us call this hypotenuse AC to be B. Then you can see that x equals B cosine of theta. Therefore, delta x is going to be B sine theta delta theta. I am just worrying about the magnitude, so this sine minus sine I am not worrying about. Y equals B sine theta, and therefore, delta y is going to be B cosine of theta delta theta, and therefore, delta y over delta x is going to be equal to cotangent theta, or delta y is equal to delta x times cotangent theta. How much is delta x? That is equal to nothing but the change in the length AB for rotation. Let me just write on the side, rotation 2 pi change in AB is equal to L. So, for delta alpha it is going to be L over 2 pi times delta alpha. So, therefore, delta y is L over 2 pi cotangent theta delta alpha divided by 2. This divided by 2 comes because change in x equals AB divided by 2. So, delta x is delta AB divided by 2. So, we have calculated the change in delta y related to a change delta alpha. Since in this screw jack there are 4 lengths like these, 1, 2, 3, 4. So, for delta alpha the change in the height of the jack is going to be equal to 4 times delta y, which is 4 times L over 2 pi cotangent theta delta alpha by 2. This 2 cancels with 4, and this is therefore L over pi cotangent theta delta alpha. Let us now calculate the total virtual work done. Total virtual work done is going to be C times delta alpha because of the torque, and the length y increases in the direction opposite to W. So, this is going to be minus W L over pi cotangent theta delta alpha, and by the principle of virtual work this is 0, and that gives me an answer that the torque that is required to lift the weight minimum has to be W L over pi cotangent of theta, and that is your answer. So what I have done in this lecture is given you an introduction to the method of virtual work for you to appreciate the power of this method. It bypasses doing lengthy calculations and focuses directly on the external forces that we want to calculate. Of course, we have not included friction here because friction is a constraint force that does virtual work. You will be learning about more advanced techniques using such methods in the future courses.